Okay, wave properties. There are 5 properties that you may remember from physics last year, but we're going to go over them again. First one, rectilinear propagation, which isn't as painful as it sounds. Waves travel in straight lines. So whether you're talking about linear waves or circular waves, all waves travel in straight lines. For linear waves, it's pretty obvious. Those waves move in a straight line. Circular waves, if you think about it, every circle is an infinite number of straight lines going out in all directions. So it doesn't matter if it's a linear or a circular wave, all of those waves are traveling in straight lines. Okay. Interference. Waves can be in the same place at the same time. Basically, because waves are energy, they can pass through each other. They don't have the same restrictions that matter does. So there are 2 types of interference. There is constructive interference. That's when waves combine to make a bigger wave, and destructive interference when waves combine to make a smaller wave. And that leads us to the principle of superposition. When 2 or more waves overlap, the net disturbance is the sum of the individual disturbances. The direction, I guess, the orientation is relevant here, because if there's a wave on top and a wave on the bottom, they've got a different orientation that's going to create destructive interference. So when 2 waves on the same side add together, they make a bigger wave. When 2 waves are on the same side, they add together to make a bigger wave. When they're on opposite sides, they kind of cancel each other out to create a flat wave. Okay. And that is the principle of superposition, which is all about interference. Reflection. Waves bounce off of surfaces. The law of reflection, which we'll get more into when we do optics in the spring. If you remember, the angle of incidence, angle I, is equal to the angle of reflection, angle R, with respect to a line that's normal to the surface. Now again, these 2 angles are on the inside of your V. If the surface is flat, it's also true that these angles out here are equal, but it's only if the surface is flat. And the law of reflection has to apply on any surface, even a surface that looks like this. And so you can't use that assumption that the outside angles are equal when you've got an uneven surface like that. And so that's why we really stick to the normal line when we're talking about angle of incidence and angle of reflection. Okay, now reflection also includes bouncing off of barriers. So you have a fixed end, which is attached to some surface, or you have a free end that is loose. Think of it as a ring on a pole that's allowed to slide up and down. Okay, so fixed and free ends. Now, if I have a wave, a shark fin wave, that bounces off a fixed barrier, so if we have a wave that bounces off a fixed barrier and it comes back with a fixed end, it flips and turns around. So if I use this as my example, the first thing I'm going to do is I'm going to flip it up, down, so it goes upside down, but it also turns like this. So it flips upside down and then it turns around. Okay, now over here, if I have this thing on a free end, what happens is it doesn't flip because the ring basically goes up and down. The end of the wave, the end of the material is allowed to move freely, and so it doesn't flip. It's not forced to go the other way. And so it just turns around. So I go flip, left, right. It turns around and keeps going. Because of the free end, it's not forced to go the other way. It's not forced to turn upside down. Okay. Standing waves. If you have a fixed end and the incoming wave hits the barrier at equilibrium, the reflected wave lines up with the incoming wave to create an increase in amplitude. So if I have a wave coming in, it's coming in, oh, there's a barrier, and it hits right at equilibrium. That reflected wave, because it's a fixed end, it's going to flip and turn. And so it's going to come out like this. Now it's important, it has to hit at equilibrium, otherwise it's not going to line up on the way out. So this does create a dramatic increase of amplitude. I know last year you guys did calculations with standing waves and you know the data table where you had 1, 2, 3, 4, 5 bubbles. We're not going to do that. You just have to understand how this stuff works. Refraction. Waves bend when they change medium. So when you have, let's say, a fast medium, and you go to a slow medium, the energy of the wave doesn't travel as fast, and so it kind of gets bunched up. And so if you look at it, let's say here's the marching band, it's going along, do 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 do, and all of a sudden they hit mud. And so the people over here start to lag behind, and every row starts to lag behind, and the longer they go through the mud, the farther behind that they get. And what it does is it changes the direction of the wave. Now, going from a slow to a fast medium, they're going along do 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 do, and all of a sudden the fast medium allows them to go faster, so the people over here speed up and they get to go faster, and the longer they're in this medium, the farther ahead they're going to get, and that changes the direction of the wave. So refraction, waves bend when they change medium. In other words, they change direction. Okay. Diffraction, waves spread out. So what happens here is that the energy of the wave gets squeezed through the narrow opening and has room to spread out on the other side. So all this energy over here gets sent through this narrow opening here, and on the other side it has to spread out. It's basically pushing itself out, and so it goes in all directions. Okay, so here's the thing, diffraction, basically, you know, the thing to keep in mind here is that the opening, oh, if I could spell the word opening, the opening is relatively small compared to the wavelength. So in the Ripple Tank lab from last year, in the Ripple Tank lab, let's say this was your wavelength. The opening, if the opening was smaller than your wavelength, you got to see the diffraction is a little more obvious. I know some students, and you might have been in one of these groups, where they had their barriers really far apart, and the waves don't get squeezed because the wavelength and the gap the gap is not smaller than the wavelength, and so you don't really see that diffraction going through. So the opening has to be basically smaller than the wavelength in order to see this bending, because the energy is getting squeezed in. We'll study diffraction in more detail when we get to light. All right, let's do Ninja Squirrel Productions. Okay, wave properties.